Yeah, thank you very much. Thank you, Zbigniew, for giving me this opportunity here to present this talk, which is related to pointing some problems in literature and maybe to finding the way how to get rid of these topics. I will not use the chance to win this $1,000. I think Professor Alicki also lost the chance to win it. I will not tell anything about electrochemistry. But since spectroscopy of semiconductors is also strictly related to the problems of photoactivity, of PN junctions, of semiconductor crystals and so on, I think it is quite important to have an idea how to measure correctly the bandgap energy, which is one of the basic parameters which we use to describe a semiconductor. For instance, my work is mostly located in the field of photocatalysis, where we use redox properties of excited semiconductors. So for us, two independent numbers are usually most important. The energy of electrons which are excited to the conduction band, or in other words, electrochemical potential of the bottom of the conduction band, and the potential of the top of the valence band. And of course, these two numbers are, when we subtract one from the other, we should get the bandgap energy. So, depending whether we want to have the material which allows us to photocatalyze strongly reductive or reduction demanding processes, we rather look for semiconductors with a high position of the conduction band edge. If we want strong oxidants, we are looking at low-lying valence bands. Yeah? But also, always the first thing which we take into account is the bandgap energy, which says us in which range, in which spectral range the material can be photoactive. But this is, of course, oversimplified picture. So to make the story a bit more complex, we have to keep in mind that the picture of conduction and valence bands are not so easy. We just do not have certain energy where conduction band starts or valence band ends and nothing else, nothing in between. We have some density or local density of electronic states. For instance, we have one anatase TiO2 crystals, which depending on which plane we focus on, we can perhaps find out that different facets, different planes are characterized by different electronic state distribution. So, to make it even more complex, we can imagine that the same crystalline phase can offer us a variety of different crystals with different planes exposed. So the situation gets really complex. A lot of electronic states. So for instance, we don't know whether we have electrochemically or photoelectrochemically or photocatalytically active states which are located just below the conduction band, or maybe these states are more important which are deeper, and so on and so on. So looking at this picture, it's even difficult to say where is our bandgap. Yeah? How to decide what it is. In principle, it should be the difference in energy between the top of the valence band and the bottom of the conduction band. And we can characterize it this way, but always keep in mind that we never have ideal crystals. Oh, I even didn't mention, when our crystal is not perfect, when we have some defects, surface bulk defects, some dopants, the situation gets even more complex. Okay, so depending whether we have semiconductors with direct or indirect band gap, we can have photon absorption or photon emission related to recombination of electrons and holes, which is associated just with the photon emission, but in the indirect band gap semiconductors, we have to emit, or here maybe it's better, we have absorption arrows, so we can either have just photon absorption, but in this case, photon absorption must be associated with phonon emission or phonon absorption. So some additional requirements must be fulfilled. By the way, for photocatalysis, photoelectrocatalysis, indirect semiconductors are in principle better because they do not, the electrons with holes do not recombine in principle so easily. So for direct semiconductors, we can have efficient emission of photons, which is always a competitive process to our electrochemical process, which we want to have. So depending whether we have, okay, I will come back to the direct, indirect semiconductors later, and how to estimate the bandgap energy, what we should do. I think all of us will think first about UV spectroscopy, which is a technique which enables us to measure absorption properties of the materials. If we have solid states, especially if we have materials which scatter a lot of light, so we cannot just measure transmitted photons, transmitted light intensity, but we have a lot of light scattering, then we usually use the diffuse reflectance spectroscopy, which in principle should give us the same information, should inform us about absorption properties of the material. If, as I know correctly, Fotonowy sells this. This is not an advertisement which was meant to be, but now I keep in mind that once we discussed about integrating spheres with Zbigniew, and yeah, there are...
Your system is ready for this
integrate
accessory.
For this accessory, yeah. So this is a very useful accessory because when the sample not only absorbs light, but when it scatters a lot of light, to have a good signal, we have to collect somehow this scattered light, and the integrating sphere allows us to catch this scattered light and to provide them to the detector, which then can record a better signal-to-noise ratio than we could do it without this integrating sphere. So I will not go into details of diffuse reflectance spectroscopy. I would like only to mention that in this type of technique, we compare the signal recorded for our sample, usually mixed with some reference material, for instance, barium sulfate, like as an analog with solutions, we want usually to measure diluted substances, dissolved in water or in other solvents. So here our solvent is barium sulfate, usually, or magnesium oxide, and so on. And we always compare the signal recorded for our sample with the signal recorded for the reference. And dividing these two signals, we can record reflectance. And for a certain sample we can get this type of spectrum. So high reflectance means low absorption. Yeah? Low reflectance means higher absorption. A little bit similar to transmission, but to transmittance, but it's not a transmittance. We cannot convert reflectance to absorbance in the way we do with transmittance. To convert reflectance to additive function, how did you call this function? Linear
impulse response.
Yeah, so to have it, we have to convert reflectance into a Kubelka-Munk function. Yeah? And in the case of solids, therefore, we talk about Kubelka-Munk function instead of absorbance, in principle. But already collecting the correct the appropriate spectrum is difficult. Here we have two examples which show two trials to record spectra for a semiconductor which does not absorb light in more or less this range and absorbs somewhere here. In this case, we perhaps have artificially lowered this baseline, and in the red case, it is too high. It should never go above 100%. Why? Because when and this is perhaps the best spectrum, if the sample is too concentrated, you get this problem, you lose the information here, so dilution is important also. Anyway, when you use this function, Kubelka-Munk function, which is very simple function, and when you try to apply it to the correctly collected spectrum and incorrectly collected spectrum, you can see from the red we have red, from the black we have black. Yeah? The black line shows the absorption spectrum or Kubelka-Munk spectrum of a semiconductor, and the red-white shows an artificial absorbance in visible part, which is of course not true. This point, which is where we lose linear ciągłość.
This cusp or
Continuity. Thank you. Yeah. Then it comes from the fact that here we have a square. Yeah. So when we take the square of negative or positive numbers, we have this, let's say, reflection of the signal from the zero line. So of course we have to avoid it, and we have to collect the right spectrum, and therefore it is so important to properly prepare the reference sample and the measured sample. Only then we can reach to the reliable absorption spectrum, which is the black line. But this is only one problem, and I will go to other problems related to the determination of the bandgap energy, because when we have this spectrum, we still are not able to say precisely where is our bandgap energy. We know that perhaps it is somewhere here, because somewhere here the material starts to absorb. To solve this problem, we can use so-called Tauc transformation. It's quite an old theory from 50s, I think, developed by Tauc, not Tauc. This is a Czech surname, so the proper pronunciation is Tauc. And according to this theory, we should have a simple transformation of the spectrum. So absorbance or Kubelka-Munk function or absorption coefficient multiplied by the energy of photons is equal to this difference. So energy of photons minus bandgap energy, which we want to determine, to the power n over 2, where n is equal to 1 or 4, depending whether we have direct band gap or indirect band gap. So such transformation of this spectrum to this one gives us a certain, or should give us at least, a certain linear part of the spectrum, and extrapolating it to the zero, we should read the band gap energy here. The theory says this, and it is broadly used, and in many papers you can find application of this theory to calculate this band gap energy. So this is a typical value for TiO2 material. But the problem appears when we modify our sample in such a way that instead of only absorption of neat semiconductor, we have also a pre-absorption bands. For instance, if we modify surface with some dyes, if we dope material with some anions, and so on, we can very easily observe visible light absorption, which changes the spectral features. And now, when we look in literature, especially I don't give citations here, because I think these authors would not like to see these examples, which show what happens. For instance, TiO2 modified with different amounts of catechol, some extrapolations are made. The very trivial error is already that zero line is here, not here. The authors didn't notice it, yes, and the conclusion in the paper is that modifying the surface of TiO2 with catechol, we can change the band gap energy from, let's say, 3.1 to 1.8 electron volts, which is of course nonsense. Another strange analysis is shown here. Yeah. So the next part, I would like to present our paper, which was submitted, which was published in the Journal of Physical Chemistry Letters, which we were very surprised within 3 years. It received something like 1,000 citations. And in this paper, we deal with this problem because this simple method can be applied only when there is no pre-absorption band or Urbach tail or any modification which changes the spectrum in this range. I will skip it because this is already shown. So for instance, we have these 3 examples, unmodified and 2 modified materials. So of course band gap energy is not changed in this way, that it lowers by 0.3 electron volts like in this case. But we should use another approach to correctly determine such energy. And we did a very simple experiment. I will describe only one experiment here. We have selected methyl orange as a dye and titanium dioxide as a semiconductor, and we prepared 2 pellets with barium sulfate as the reference material. In one pellet, we mixed all components together. So there was a mixture of methyl orange, titanium dioxide, and barium sulfate. You see, it looked like this. And this pellet was divided by 2 parts. Here we had only titanium dioxide with barium sulfate, no methyl orange. And here we had only methyl orange with no titanium dioxide. So we have separated in space titanium dioxide from methyl orange. And we have recorded spectra. So with the letter plus, I describe this situation with this straight line. I describe this situation for the clarity of the next slides. We have here titanium dioxide spectrum with a bandgap of 3.2 something. We have here the spectrum of methyl orange. The same is here. These two spectra are also here. And the other spectra are collected for these two situations. We moved a little bit the palette. Therefore, the spectra are not identical. For instance, some of them collect more from the white side, the other more from the orange side. And we apply, we transformed the spectra to Kubel-Kammung function, then we applied the Tauc transformation, and we can conclude that in these cases, modifying surface of titanium dioxide with methyl orange slightly changes the band gap energy by, let's say, 0.2, 0.25 electron volts. But surprisingly here, by placing close together, but without any contact, titanium dioxide with methyl orange, we strongly influence the band gap energy by the presence of methyl orange by something like 1 electron volt even. Yeah, of course it's a nonsense, yeah? But it clearly shows how wrong can our measurements be. Oh, no, measurements are correct. The interpretation is wrong, yeah. So what should we do? Of course, if we have absorbance or Kubel-Kammung function, then from the mixed material, we should first subtract the component which disturbs. So from the spectrum of this material, if we subtract the spectrum of methyl orange, we should get spectrum of titanium dioxide. And this is this spectrum. No, sorry, this is titanium dioxide, this is methyl orange, and this is the mixture. And when we consider that this is a linear combination, so the spectrum of the semiconductor is the spectrum of the mixture minus spectrum of the modifier. And we can get more or less this, and when we determine the bandgap energy, we get the right value, 3.18. Of course, there are some small problems here with noise and so on, so perhaps we cannot subtract it perfectly. But this is what we should do. From the spectrum of the wall material, we should subtract the spectrum of the modifier.
How about when you don't know the original sample? I mean, then you don't know how much to subtract, right? Because you may be getting rid of features of the very sample you.
Yes. Therefore, I have the next slide.
You discussed before.
No. So just the next slide will be this one. Here I just show the results. What happens to all these spectra which are presented here, yeah, when we subtract methyl orange. So it doesn't matter if we have a real mixture or if we have just these two parts, really more or less we get the right value. Okay, and now what happens if we don't know what to subtract, yeah? And this is the most common case, in fact, because it's no problem if we sensitize TiO2 or mix TiO2 with some known compound, but after, I don't know, calcination, even after adsorption, the spectrum changes, yeah, of the dye. So usually we don't know what to subtract. Then we should consider how to calculate the bandgap energy in such a case. So this is a part of this paper. Let's assume that our transformation, this is the Tauc equation, yes. Here we, instead of the absorption spectrum of the material, I add the sum of absorption spectra of the semiconductor and of the modifier. Yeah? So absorption spectrum multiplied by energy should give this. Okay, then this is for direct bandgap semiconductors. For indirect bandgap semiconductors, I should use square root. In this case, we can easily a plus b square is a square plus b square plus 2ab. We can easily do this transformation. Here, with the square root, we can use the Taylor series to change this equation to such equation. They look quite difficult, but look, we are interested in finding the bandgap energy of a semiconductor only. We are not interested in all components with the index m, but of course they are not equal to 0. But if they are equal to 0, look here, if this is equal to 0, we have exactly our equation which we want to have. Spectrum of the semiconductor times energy. And here we would also have spectrum of the semiconductor times energy, because if alpha m is 0, this disappears, this disappears, this disappears. So if alpha m is equal to 0, we are on the safe side. So we can do graphically very simple thing. We can subtract it by extending this absorption line, this and this way, and we can read the bandgap energy here at these crossing points, not here. And in this way, we can reach our goal. We got rid of the spectrum of the modifier, unless it suddenly changes at this point. If our modifier changes its spectrum in a non-continuous way, yeah, here we perhaps can be mistaken. But otherwise, we have very good results, very good approximations. Just to show you some examples, we have different materials. So rutile TiO2 has this bandgap energy, and here iron doped TiO2 rutile or vanadate doped rutile with the Tauc plot transformation, without the correction, we got lowered numbers. So again, we could conclude the bandgap energy was changed. But if we apply this baseline approach, we got these values, which are quite similar to this one. Here we have catechol TiO2, the example which I have shown. Nothing changes, but it changes here. Or the mixture or composite of two semiconductors, cadmium sulfide and TiO2, which is shown here. TiO2 bandgap energy should be read here, and yeah, for different samples, we always got the same value, while here we could be mistaken. Yeah, here you can see it's below 3, which is the mistake. Of course, from this plot we can also determine the bandgap energy of cadmium sulfide, which will be quite okay, because this Urbach tail is rather low. Yeah, so you can see I tried to show you not only experimentally, but I tried to provide some mathematical arguments that this method allows you to determine correctly the bandgap energy. And of course we should use the Tauc theory, the Tauc transformation, Tauc plots, but we should do it consciously, and we can, or we should apply it in the right way. Yeah, that's all I wanted to tell. This is the picture taken at the roof of our faculty, a group of photocatalysis. Actually, one person is here. The other will come. And I would like to thank the group. I should thank also for the support. And I would like to thank all of you and to Zbigniew especially.
All those measurements were done on powder samples, right? For TiO2 with additions.
Yes.
All right. And I'm surprised that those slopes were that sharp after all, because I would think that the defects would smear out all the.
I have selected the. I don't want to say the best results. I have selected titanium dioxide as the material because it usually gives clear spectrum, clear spectra. But we can apply it also to direct semiconductors. These were examples with indirect semiconductors. With direct semiconductors, it works as well.
I would like to have a question about the general validity of the Tauc approximation, because in general, if we have a direct or indirect semiconductor as a one body, I would say, it is clear which coefficient n to choose, right? We have some constants from the theory, but it is not so clear which values should I choose when I have a modified layer or group mixture of semiconductors or some complex, some complex case. So what should we do in this case?
There are different approaches. One of them is, if you don't know if you have direct or indirect semiconductor, you should apply both transformations, and either square root or square will give you linear part. Yeah.
The bad part is when I do not have a straight line in any case.
Yes.
Or only in both cases.
Yes. This was one approach. Yeah. Sometimes it works. Sometimes you can find also another approach where people give just both values. So they don't care what is the real situation. They give values for direct and indirect measurement, which somehow also can work. Yeah.
Yes.
But I don't have a good solution for this. Yeah.
Okay, thank you.
So thank you. Sorry.
And also, what will be if you use just absorbance spectrum, and you also take the linear part and also this background, but not parallel to the XY, but just also such not linear.
Yes.
Not as slow.
Yes. So
For such problematic
can make
cases,
these two lines.
For example, it is like absorbance spectrum,
Yes.
and don't use Tauc's approach.
So here, when I showed you all these mathematical transformations, I had to assume that the spectrum of the mixture is a sum of the components. And it is true for absorbance and for Kubelka-Munk function. Yeah? So that's why you have to have these additive functions. Then everything should work fine.
Yeah, it is especially important when you are not able to prepare such sample with mixture. If you have something on the substrate and some.
You can subtract whatever. Just transform your. If you have transparent electrodes, for instance, you can measure directly absorption spectrum in absorbance and use the same methodology.
Any other questions? So thank you again.
Thank you.